Okay, this is number 5 from the 2013 AP Physics B exam, and this is a thermodynamics problem. In a certain process, 3,200 joules of energy is added to an ideal gas by heating. During the same process, 2,100 joules of work is done on the gas. It's really important to pay attention to ons and bys throughout AP Physics problems. I'm glad they underline it. They don't always do that, so really make sure you're understanding if it's on the gas or by the gas. So A wants us to determine the change in internal energy of the gas itself. So internal energy of a gas is always going to be equal to Q minus the work done by the gas. Now some of you may have been taught that it's plus W. That would mean the work done on the gas. Here's the work in this situation by the gas. It does get a little tricky. So I like to think it through kind of in a sense like common sense like manner. If 3,200 joules is added to the gas by heating, its internal energy is going to try to go up. That's for sure. We're heating it. Its internal energy is going to try to rise. Now, it doesn't always rise. It really depends on if the gas itself is doing work as well. And in this case, it's not. 2,100 joules of work is done on the gas, which implies some outside source is basically compressing the gas into a smaller space. So both the 3,200 joules and the 2,100 joules are driving that internal energy up. So, I mean, if we were to write it out algebraically or arithmetically, it would be nice and easy. You have 3,200 joules for your Q value. And again, this is minus the work in terms of it being by the gas. And this is 2,100 joules on the gas. So when it's positive 2,100 on a gas, it's always going to be negative 2,100 by the gas. And a negative of a negative is a positive. So we're going to do 3,200 joules plus 2,100 joules to get our final internal energy change of 5,300 joules. Okay, and that's going to be a 1-pointer. Part A was just the 1 point. I should label this just in case I need to refer back to it. Alright, B. Indicate whether each of the following properties of the gas increases, decreases, or remains the same during this process. So let's kind of go through and think about what's happening here. What's happening to the volume? Well, if work is being done on a gas, that gas is getting compressed into a smaller space. Understand that work is force times change in displacement, and I can go through the whole proof here, blah, 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 blah. Ultimately, you get down to this whole pressure delta V bit, and if the displacement is shrinking or the volume is going down, then something must be compressing it or doing work. So if work is done on something, its volume must decrease. So first and foremost, volume is decreasing. Again, justify it. I would encourage you to try to justify it using a combination of both sentences and the equation. You may want to go ahead and just say work is P delta V. And since your work by the gas is negative, the delta V is negative. Or you may recall work is negative P delta V, and that's the case when we have it dealing with on a gas. Again, this on and by stuff tends to get a little confusing. So if it's negative P delta V, then we're going to treat W as positive, as it was, 2,100 joules. And that implies a negative positive change, which means the volume decreases. However you want to word it, however you want to look at it, volume decreases. Now what happens to the temperature? Well, temperature and internal energy, it's great when they ask these kinds of problems because U is proportional to really only two things. If we write out our actual U equation dealing with the internal energy of a gas, it's 3/2 nRT. And so your internal energy of a gas will vary by the amount of gas you have. That should make sense. You have more gas, you have more internal energy, more particles that carry their own individual energies. And then temperature. So if temperature goes up, your internal energy also goes up. Well, the amount of gas in this situation won't change. It would very clearly tell you that the amount of gas is changing. It'd say there's a leak, or it'd say it's adding to the gas, blah, 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 blah. So really, U is proportional to T. And so if our internal energy is driving up, then our temperature is driving up. And again, I'll let you worry about how to justify that using your own wording and math and whatever. And then finally, the pressure. What's happening to the pressure of the container? And you can go and try to use equations and numbers and have that help conclude for you, or you can just think about it. we have a container, we're shrinking its volume, and at the same time we're shrinking its volume, we're heating the gas up. When we take that container that had particles occupying a large amount of space, and then we compress it and have the same number of particles, so all of these guys that are up here are really down here now, and that container is actually not as tall anymore, maybe is the best way of illustrating it with my program that I have here, and I'm sorry I can't do anything fancier than that, but picture that. The amount of particles are now getting squeezed into a smaller space, and so they would normally be driving the pressure up, and as long as heat can't leave, or their internal energy doesn't drop, the pressure will go up. Not only that, it's the other way around. Heat isn't leaving, heat's being added, so we're adding heat, squeezing them in. Your internal energy is going to rise up too, but more importantly, your pressure will rise up. We have an increase in pressure. B was worth, each part was worth 2 points, so take your time on this. 2 each, make sure you're justifying it, make sure you're indicating the right spot, the right change. That's 6 whole points out of the 10, right there. No real math needed to happen up here. Okay, now let's suppose in a different process, 1800 joules of work is done on the gas. At constant temperature, this is really important to pay attention to, because now C, determine the change in internal energy of the gas. Well, if we look at this up here, we recognize, as I already showed, internal energy is proportional to temperature. Well, if temperature stays constant, internal energy needs to stay constant. So the answer to part C, no change, or remains the same, or whatever, delta U equals 0. Part C was worth 1 point. And then finally, part D. Which of the following correctly describes the energy transfer by heating, if any, between the gas and its surroundings? Let's go back to that first equation that I wrote down. U equals Q minus W. That means Q equals W. Why do I am able to do it? Well, because I know U won't change. We just said that. So, any work done needs to equal the heat. And so I guess the only question now is, the work done will equal the heat added, or the work done will equal the heat loss? Well, I mean, let's think about it. We're doing 1800 joules work on the gas. We're basically squeezing it into a smaller space. That's trying to drive the internal energy up. In order for the internal energy to stay the same, heat needs to leave the container. Therefore, energy is definitely transferred out of the gas. Again, that with proper justification will make it a 2-point problem. I highly encourage you to look through your rules, make sure you define on and by properly, and don't get overwhelmed by all these words.